At the beginning of the 20th century, physics stood on a proud foundation. Newton's mechanics had explained motion for centuries, Maxwell's equations had unified electricity and magnetism into a single elegant framework, and thermodynamics had revealed the deep rules governing energy and heat. Scientists believed they were closing in on a nearly complete description of nature. Atoms had been confirmed as real, electrons had been discovered, and the inner architecture of matter was slowly coming into focus. Yet beneath this confidence, tiny cracks had begun to appear, small experimental results that did not fit neatly into the grand structure of classical physics. One of the most troubling clues came from light itself. When scientists heated elements or passed electric currents through gases, the atoms emitted light at very specific colors, forming patterns called spectral lines. These lines acted like fingerprints for each element. By the late 1800s, spectroscopy had become one of the most precise tools in physics. Researchers could measure the wavelengths of these lines with extraordinary accuracy, and they began to notice something unsettling. Under certain conditions, single spectral lines split into multiple closely spaced lines. This effect became especially clear when atoms were placed in a magnetic field, a phenomenon known as the Zeeman effect. The Dutch physicist Pieter Zeeman observed in 1896 that spectral lines broadened and split when a magnetic field was applied. Hendrik Lorentz soon explained this behavior using classical ideas, suggesting that electrons inside atoms moved in orbits and that magnetic fields altered these motions slightly. His theory predicted a specific pattern of splitting, and in many cases it worked well. This was called the normal Zeeman effect. For a moment, it seemed that another mystery had been neatly folded into the existing framework. But nature was not so cooperative. As experimental techniques improved, physicists encountered many examples of the anomalous Zeeman effect, where the splitting did not match Lorentz's predictions at all. The lines divided into unexpected numbers of components, with spacings that defied the classical model. The anomaly was not rare, it was widespread. The word anomalous itself reflected the frustration of scientists who could label the problem but could not solve it. Something fundamental about electrons inside atoms was missing from their understanding. At the same time, another revolution was unfolding. Max Planck's work on blackbody radiation in 1900 and Albert Einstein's explanation of the photoelectric effect in 1905 had introduced the idea that energy could come in discrete packets, or quanta. Niels Bohr, in 1913, proposed that electrons in atoms occupied specific quantized orbits, explaining the hydrogen spectrum with remarkable success. His model marked the birth of quantum theory, yet it was still a hybrid. Electrons were imagined as tiny planets circling a nucleus, obeying classical mechanics, except for certain allowed energy levels. Bohr's theory handled hydrogen well, but for more complex atoms it struggled. Arnold Sommerfeld extended the model by allowing elliptical orbits and introducing additional quantum numbers to describe them. These refinements explained fine structure, small splittings in spectral lines caused by relativistic effects, and subtle variations in electron motion. For a time, it seemed the pieces were coming together. Still, the anomalous Zeeman effect remained stubbornly unexplained. Even the improved quantum models could not account for the detailed patterns seen in magnetic fields. Physicists were forced into an uncomfortable position. They had equations that worked in many situations, yet a growing list of precise measurements contradicted them. The anomalies were not random noise. They followed systematic patterns. Spectral lines split into doublets and triplets in ways that hinted at some hidden two-valued property of the electron. It was as if the electron carried an extra label, something beyond charge, mass, and orbital motion. In 1924, Wolfgang Pauli confronted this chaos. Known for his sharp mind and relentless criticism, Pauli analyzed atomic spectra and proposed what he called a classically indescribable two-valuedness associated with the electron. He did not know what this property physically was, but he was convinced it existed. Using this idea, he formulated the Pauli exclusion principle, stating that no two electrons in an atom could share the same set of quantum numbers. This principle successfully explained the structure of electron shells and the periodic table, yet the mysterious two-valued property remained a placeholder, an admission of ignorance disguised as a rule. The stage was set for a breakthrough, but it would come from an unexpected direction. In 1925, two young graduate students in Leiden, George Uhlenbeck and Samuel Goudsmit, were discussing atomic spectra under the guidance of Paul Ehrenfest. They considered the possibility that the electron itself might possess intrinsic angular momentum, like a tiny spinning top. This internal rotation could produce a magnetic moment, explaining why electrons responded to magnetic fields in ways the orbital models could not capture. The idea was daring and simple at the same time. If the electron carried its own angular momentum, independent of its motion around the nucleus, it would naturally have two possible orientations in a magnetic field. This could account for the observed doublets in spectral lines and provide a physical basis for Pauli's mysterious two-valuedness. Uhlenbeck and Goudsmit proposed that the electron had an intrinsic spin. Their proposal was not immediately welcomed. When they calculated the implications using classical physics, a serious problem appeared. To generate the observed magnetic moment, a spinning electron would have to rotate so fast that parts of it would exceed the speed of light. That was impossible according to Einstein's relativity. Prominent physicists, including Lorentz, initially objected. The model seemed to violate fundamental principles, yet the data refused to go away. The spin idea, despite its classical inconsistencies, matched experimental results with striking accuracy. Around the same time, new developments in quantum mechanics were reshaping physics. Werner Heisenberg introduced matrix mechanics, and Erwin Schrödinger developed wave mechanics. These formalisms did not rely on visualizable orbits, but on abstract mathematical structures. Within this new framework, properties did not have to correspond to tiny mechanical pictures. Paul Dirac provided the decisive step in 1928. Seeking a quantum theory consistent with relativity, he derived an equation for the electron that naturally included spin. Without adding it by hand, the mathematics predicted that the electron had intrinsic angular momentum and the correct magnetic moment. Spin was no longer a speculative mechanical rotation. It emerged as a fundamental feature of relativistic quantum theory. What had seemed impossible in classical terms became inevitable in the new physics. Looking back, the discovery of electron spin was not a single moment, but a gradual realization forced by experiment. Spectral lines splitting in magnetic fields, puzzling doublets, and the failure of classical models created pressure that theory could not ignore. Pauli's abstract rule hinted at a hidden variable, and the bold guess by Uhlenbeck and Goudsmit gave it a name and a picture. Dirac's equation then embedded spin deep within the structure of quantum reality. This episode revealed a profound lesson about science. Nature does not guarantee that its workings will fit human intuition. Physicists tried to interpret atomic behavior using familiar ideas of particles moving along paths, yet the electron possessed a property that had no true classical analog. The word spin survived, but its meaning changed. It no longer described a tiny object physically rotating in space. It referred to an intrinsic quantum degree of freedom, encoded in mathematical symmetries. The historical puzzle of spectral line splitting thus led to a revolution in understanding. A discrepancy measured in laboratory magnets forced physicists to expand the very definition of what a particle could be. The electron became more than a point charge. It became an entity with internal quantum structure, even if that structure could not be visualized. From confusion and anomaly emerged a deeper layer of reality, one that would shape the rest of 20th century physics. By the time spin was fully accepted, the old dream of explaining everything with classical pictures had faded. The discovery marked a turning point where abstract mathematics, guided by stubborn experimental facts, revealed properties that defied everyday experience. The electron's spin, born from a historical puzzle, became one of the cornerstones of modern science, showing that even the smallest inconsistencies can open doors to entirely new worlds of understanding. When people first hear the word spin, the mind reaches for something familiar: a spinning coin, a rotating planet, a toy top whirling on a table. Motion in circles is one of the oldest and most intuitive ideas in physics. For centuries, angular momentum meant an object turning around an axis in space. So when scientists say an electron has spin, the natural reaction is to imagine a tiny charged sphere rotating rapidly. That picture feels comfortable, mechanical, and easy to visualize. It is also deeply wrong. The difficulty begins with the nature of the electron itself. In everyday life, spinning objects have size and shape. A football spins because different parts of it move through space along circular paths. But experiments show that the electron behaves, as far as we can measure, like a point particle. It has no known internal structure, no surface we can see, no measurable diameter in the classical sense. If something has no size, what would it even mean for it to rotate? Rotation usually describes different parts of an object moving at different speeds around a center. With an electron, there are no parts to track, yet the electron undeniably carries angular momentum. Measurements of atomic spectra, magnetic interactions, and quantum transitions all reveal that electrons behave as if they possess an intrinsic form of rotation. This is not optional or accidental. It is as fundamental to the electron as its electric charge. The challenge is that this angular momentum does not arise from motion through space in the usual sense. It arises from the deeper mathematical structure of quantum theory. In classical physics, angular momentum is defined by mass in motion. An object of mass moving in a circle carries angular momentum proportional to its mass, speed, and distance from the axis. In quantum physics, angular momentum still exists, but it appears in a more abstract way. Systems are described not by definite trajectories, but by wave functions, mathematical objects that encode probabilities. These wave functions can possess symmetries under rotations, and those symmetries give rise to quantized angular momentum. Electron spin is a form of intrinsic angular momentum that does not come from the electron orbiting something else. It is built into the type of wave function that describes an electron. In fact, electrons are described by entities called spinors, which behave in a peculiar way under rotations. If you rotate a classical object by 360 degrees, it returns to its original configuration. A spinor requires a full 720 degree rotation to come back to the same state. This strange property has no classical analog, yet it is essential for understanding spin. One of the key differences between classical rotation and quantum spin is quantization. In the classical world, angular momentum can take any value. A wheel can spin slowly or quickly, with a continuous range of possibilities. Electron spin, however, comes in fixed amounts. The electron has a spin quantum number of 1, half. This does not mean it spins at half speed or half a turn. Instead, it refers to the magnitude of its intrinsic angular momentum, which has a precise value determined by fundamental constants. There is no spectrum of allowed spin magnitudes for the electron. It always has the same amount. Even more striking is that when we measure the component of an electron's spin along a chosen direction, we find only two possible results. If we set up an experiment to measure spin along a vertical axis, we will detect either up or down, never something in between. This was dramatically demonstrated in the Stern-Gerlach experiment in 1922. When a beam of silver atoms passed through a non-uniform magnetic field, the beam split into two distinct parts instead of forming a continuous smear. This showed that the magnetic moments associated with electron spin could align only in discrete orientations. This two-outcome behavior is one of the clearest signs that spin is not classical rotation. A classical spinning object could point its angular momentum in any direction, producing a continuous distribution of measurements. Quantum spin is constrained by the rules of quantum mechanics. Before measurement, the electron's spin can exist in a superposition of up and down states. Only when measured does it choose one of the allowed values. The act of measurement itself plays a role, something that has no parallel in classical mechanics. Another reason the literal spinning sphere picture fails is relativity. If we try to calculate how fast the surface of a tiny electron would need to move to produce the observed magnetic moment, we find speeds greater than that of light. This contradiction shows that the magnetic properties of the electron cannot be explained by charge circulating in a physical loop. Instead, the magnetic moment arises directly from the quantum equations describing the electron. It is an intrinsic feature, not the result of internal motion through space. Mathematically, spin is represented using operators that obey specific commutation relations. These relations define how different components of spin interact when measured along different axes. The structure mirrors that of ordinary angular momentum, but with key differences tied to the half integer value. The algebra leads to the conclusion that spin of particles, like electrons, require a special type of transformation under rotations. This abstract framework, though far removed from spinning tops, accurately predicts experimental outcomes with extraordinary precision. Spin also connects to a deep principle in quantum field theory, the distinction between fermions and bosons. Particles with half-integer spin, such as electrons, protons, and neutrons, are fermions and obey the Pauli exclusion principle. Particles with integer spin, like photons, are bosons, and can occupy the same state in large numbers. This link between spin and statistical behavior is known as the spin statistics theorem. It shows that spin is not just a minor property, but a defining feature that determines how matter itself is organized. Despite its abstract nature, spin produces very tangible effects. The magnetic behavior of materials, the structure of atoms, and the stability of matter all depend on this quantum property. Yet at its core, spin remains a reminder that the quantum world does not conform to mechanical imagery. Words borrowed from everyday life are used, but their meanings shift, spin, survives as a term because it captures the idea of angular momentum, but the mechanism behind it belongs to a different conceptual realm. Understanding spin requires accepting that not all physical properties correspond to motions we can picture. Some arise from the symmetries of nature at a fundamental level. The equations of quantum mechanics and relativity dictate that particles like electrons must carry intrinsic angular momentum. This property manifests in measurements, interactions, and technologies, but it does not involve little spheres twirling in space. In this way, electron spin marks a boundary between classical intuition and quantum reality. It forces us to move beyond visual metaphors and trust the predictive power of mathematical structure. The electron is not a tiny rotating object, yet it behaves as though it has a built-in rotation. That paradox is not a flaw in the theory, but a sign that the universe operates on principles that are deeper than everyday experience. Long before scientists understood the inner structure of the atom, they already knew that certain properties of matter seemed permanent and unchangeable. Mass did not vary from one measurement to the next. Electric charge came in fixed amounts, with the electron always carrying the same negative value. These properties were not behaviors that switched on and off depending on circumstances. They were part of what the particle was. As quantum theory developed, physicists realized that electron spin belongs in this same category. It is not something the electron does. It is something the electron is. In everyday language, we often describe properties in terms of actions. A wheel spins, a planet orbits, a current flows. These are motions, processes that can start, stop, or change speed. But intrinsic properties are different. They are built into the identity of a particle in the same way a number is built into a mathematical constant. You cannot take the 3ness out of the number 3. Likewise, you cannot remove charge from an electron or reduce its mass to 0 without changing it into something else entirely. Spin stands alongside these quantities as a fundamental descriptor. This realization marked a shift in how physicists thought about particles. Early atomic models treated electrons almost like tiny mechanical objects, little bits of matter moving in space. Over time, experiments revealed that electrons behaved less like miniature billiard balls and more like excitations of underlying quantum fields. In this picture, an electron is a localized manifestation of an electron field that fills the universe. The properties of the electron, mass, charge, and spin are determined by the nature of this field. They are not add-ons. They are consequences of the type of entity the electron is. Spin, in this context, emerges from the symmetries of spacetime itself. The laws of physics remain the same when we rotate our coordinate system, a principle known as rotational symmetry. In quantum theory, particles must transform in specific ways under these rotations. The electron belongs to a class of objects whose mathematical description requires a spin, a representation of the rotation group. This is not a choice made by the electron. It is a statement about the structure of the theory and the observed behavior of nature. Because the electron transforms this way, it necessarily has intrinsic angular momentum. Comparing spin to charge helps clarify its status. Electric charge determines how strongly a particle interacts with electromagnetic fields. We do not imagine charge as a tiny object glued onto the electron. It is a parameter appearing in the equations that describe how the electron field couples to the electromagnetic field. Similarly, spin determines how the electron responds to rotations and magnetic fields. It governs the form of the electron's wave, function, and the algebra of the operators that describe its behavior. In both cases, we are dealing with built-in characteristics, not optional features. One of the clearest signs that spin is intrinsic is its universality. Every electron, anywhere in the universe, has exactly the same spin magnitude. We have never observed an electron with spin 1, spin 0, or spin 3 halves. This uniformity mirrors the consistency of charge and mass. If spin were due to some internal mechanical structure, we might expect variations or the possibility of excitation. Instead, spin is fixed, suggesting it arises from a deeper layer of reality than internal motion. The magnetic moment of the electron further illustrates this point. When placed in a magnetic field, the electron behaves like a tiny magnet. The strength of this magnetism is directly related to its spin. The remarkable agreement between theoretical predictions and experimental measurements of the electron's magnetic moment accurate to many decimal places indicates that spin is woven into the fundamental equations. There is no room for it to fluctuate as a mechanical detail might. It is locked into the electron's identity. Intrinsic properties also share another feature. They do not depend on the environment. An electron drifting through empty space has the same spin as one bound inside an atom or flowing in a metal wire. External conditions can influence how spin is oriented or how it interacts, but they do not change the amount of spin the electron possesses. This independence distinguishes intrinsic characteristics from dynamical ones like velocity or energy, which vary with context. The concept of intrinsic spin also reshaped the definition of what a particle is. In classical thinking, a particle was a small chunk of matter with position and momentum. In quantum field theory, a particle is classified by a set of numbers that label how it transforms under symmetries. Spin is one of these key labels. Together with mass and charge, it specifies the species of particle. Two particles that differ in spin are fundamentally different kinds of entities, even if other properties are similar. This deeper perspective explains why spin cannot be gradually turned off. If we imagine reducing an electron's spin to 0, we are no longer talking about an electron. We would be describing a different type of particle, one that obeys different statistics and interacts differently with fields. The Pauli exclusion principle, which shapes the structure of atoms, depends directly on electrons being spin fermions. Change the spin, and the entire architecture of matter would change. Intrinsic spin also connects to conservation laws. Angular momentum is conserved in isolated systems. Because electrons carry intrinsic angular momentum, this conservation includes spin as well as orbital contributions. In particle interactions, spin must be accounted for just as carefully as energy or charge. It can be transferred, reoriented, or combined, but the total follows strict rules. This reinforces the idea that spin is a real, measurable quantity, not a metaphor. The language of intrinsic properties can feel abstract, yet it reflects a shift in scientific understanding. Rather than asking what an electron looks like inside, physicists focus on how it behaves under fundamental symmetries and interactions. Spin does not describe a hidden mechanism, but a category of behavior dictated by the underlying theory. It is a label that encodes how the electron fits into the fabric of quantum fields and spacetime. In this sense, spin stands shoulder to shoulder with mass and charge as a cornerstone of identity. Mass determines how the electron responds to gravity and inertia. Charge determines how it interacts electromagnetically. Spin determines how it responds to rotations, magnetic fields, and the quantum statistical rules that govern matter. Remove any one of these, and the concept of an electron dissolves. Recognizing spin as intrinsic helped free physics from the need to imagine tiny mechanical models for everything. It showed that some properties are fundamental descriptors arising from symmetry and mathematical structure. The electron is not a little object with parts that can be rearranged. It is an excitation characterized by a fixed set of numbers, among which spin plays an essential role. Through this lens, the electron becomes less like a miniature object and more like a note played by the universe's quantum field. The pitch of that note, its mass, charge, and spin, is determined by the instrument itself. These features do not change from performance to performance. They define the very possibility of the sound. Spin, then, is not an accessory but a defining tone in the music of matter. In the quiet interior of an atom, a strict order governs the behavior of electrons, an order so fundamental that it shapes the structure of every element in the periodic table. This order does not arise from classical forces alone, nor from simple electrostatic attraction between electrons and the nucleus. It emerges from a rule that seems almost philosophical in nature, a rule about identity and distinction at the quantum level. That rule is known as the Pauli exclusion principle, and at its heart lies electron spin. To appreciate its significance, imagine for a moment that electrons did not possess spin. Suppose they were identical in every measurable way, with no extra internal label. In such a universe, electrons would tend to crowd into the lowest available energy state around the nucleus. Since lower energy states are more stable, all electrons would simply pile into the same orbital, like marbles rolling to the bottom of a bowl. Atoms would collapse into extremely compact, featureless objects. The rich structure we associate with chemistry shells, valence electrons, bonding patterns, would disappear. But reality is different. Electrons carry spin, and spin provides an additional quantum number that distinguishes one electron from another. When Wolfgang Pauli studied atomic spectra in the 1920s, he noticed patterns that could not be explained by orbital motion alone. To account for these patterns, he proposed that no two electrons in an atom can share the exact same set of quantum numbers. These quantum numbers describe the state of an electron, its energy level, the shape of its orbital, its orientation in space, and its spin direction. Spin is the crucial final piece. For a given orbital, defined by the first three quantum numbers, there is room for only two electrons, and they must have opposite spin orientations. One is described as spin up, the other as spin down. This pairing is not a matter of preference, but a fundamental requirement of quantum mechanics. It arises from the mathematical properties of particles with half-integer spin, known as fermions. The reason behind this rule lies deep in the symmetry of quantum wave functions. When two identical particles are exchanged, the overall wave function must either remain the same or change sign. For fermions like electrons, the wave function changes sign. This antisymmetric property leads directly to the exclusion principle. If two electrons try to occupy exactly the same state, the wave function describing them would cancel itself out, resulting in zero probability. In other words, nature forbids it. This abstract rule has enormous physical consequences. Because electrons cannot all occupy the lowest energy level, they fill available states in a layered structure. The lowest energy shell fills first, holding two electrons with opposite spins. Once it is full, additional electrons must occupy higher energy shells. These shells correspond to different average distances from the nucleus and different orbital shapes. The step-by-step filling creates the architecture of atoms. The periodic table is a direct expression of this structure. Elements in the same column share similar chemical behavior because their outermost electron configurations follow repeating patterns. The reason these patterns exist at all is the exclusion principle combined with spin. The number of electrons that fit in each shell and subshell is determined by how many distinct quantum states are available, and spin doubles the capacity of each orbital. Without spin, the table would not have its familiar form. The stability of matter itself depends on this principle. Consider what happens in a piece of solid material. Atoms are packed close together, and their electron clouds overlap. If electrons could all fall into the same low-energy state, matter would compress dramatically. Instead, the exclusion principle creates a kind of quantum pressure. Electrons resist being squeezed into identical states, so they occupy higher momentum states when confined. This resistance contributes to the rigidity of matter and prevents ordinary objects from collapsing. This effect becomes even more dramatic in extreme environments. In white dwarf stars, gravity tries to compress matter to enormous densities. The electrons inside are forced into higher and higher energy states, generating what is called electron degeneracy pressure. This pressure, rooted in the exclusion principle and spin, can counterbalance gravity and prevent further collapse. A rule discovered while studying atomic spectra turns out to govern the fate of stars. Spin also determines how electrons pair in atoms and molecules. When two electrons share an orbital with opposite spins, their magnetic effects partially cancel, lowering the energy. This pairing influences chemical bonding, magnetic properties, and the shapes of molecules. In some materials, unpaired electron spins align collectively, leading to magnetism. In others, electrons pair up and the material is non-magnetic. Again, the simple fact that electrons have two spin states underlies complex physical behavior. The exclusion principle reveals that identity at the quantum level is subtle. Electrons are indistinguishable in the sense that no experiment can label one as permanently different from another. Yet spin allows them to occupy distinct states. The combination of indistinguishability and spin-based distinction leads to the intricate balance between sameness and difference that structures matter. This principle also shows that not all particles behave the same way. Particles with integer spin, called bosons, follow different statistical rules. They can share the same state in unlimited numbers, which is why photons can pile into a laser beam and atoms can form Bose-Einstein condensates. Electrons with spin 1/2 belong to a contrasting category. Their refusal to share states is not stubbornness, but a fundamental law of quantum statistics. The connection between spin and the exclusion principle highlights how a seemingly abstract quantum property shapes the tangible world. The arrangement of electrons in atoms, the diversity of elements, the solidity of materials, and even the stability of stars all trace back to this rule. Spin provides the binary choice, up or down, that allows two electrons to share an orbital, but no more. In this way, the exclusion principle acts like an organizing law, preventing overcrowding and enforcing structure. It ensures that electrons spread out among available states, building complexity from simple rules. What began as a puzzle in atomic spectra became a cornerstone of physics, revealing that the microscopic rules governing identical particles have macroscopic consequences. Through spin and exclusion, quantum mechanics imposes order on the universe. Matter does not collapse into uniformity, because electrons cannot all be the same in the same way at the same time. This restriction, subtle and invisible, is one of the hidden reasons why the world has form, variety, and stability. If you hold a small magnet in your hand and feel the faint pull between it and a metal surface, you are experiencing the collective behavior of countless tiny quantum properties acting together. That everyday force, so familiar it seems almost ordinary, arises from one of the most subtle features of the electron, its spin. What appears at the human scale as a simple attraction or repulsion is, at the microscopic level, a grand alignment of intrinsic angular momenta, each electron behaving like a minute compass needle. Every electron, because of its spin, carries a magnetic moment. This means it responds to magnetic fields and can itself create a magnetic field. The relationship between spin and magnetism is not an add-on to the theory of electrons. It is built into the equations of quantum mechanics. The magnetic moment of the electron is directly proportional to its spin, and its value has been confirmed with astonishing precision. This connection transforms spin from an abstract quantum number into something that can influence macroscopic objects. Inside atoms, electrons occupy orbitals around the nucleus. These orbitals determine how likely an electron is to be found in different regions of space, but they also determine how spins combine. Often, electrons form pairs in the same orbital with opposite spin orientations. When this happens, their magnetic effects largely cancel each other. Materials in which most electrons are paired tend to show little or no overall magnetism. This is the case for substances like water, wood, and many metals under ordinary conditions. However, not all electrons are paired. In some atoms, particularly those of transition metals like iron, cobalt, and nickel, there are unpaired electrons in partially filled orbitals. Each unpaired electron contributes a tiny magnetic moment. On its own, a single atomic magnetic moment is extremely small, but when many atoms interact in a solid, their spins can influence each other. The interactions between neighboring spins can favor alignment in the same direction, a phenomenon rooted in quantum mechanics and the Pauli exclusion principle. This alignment process is not due to a simple classical attraction between little magnets. Instead, it arises from what is known as the exchange interaction. Because electrons are identical fermions, the symmetry of their combined wave function affects their energy. Under certain conditions, having parallel spins can lower the total energy of the system. The result is that large numbers of electron spins spontaneously line up, producing a net magnetic field. This is the origin of ferromagnetism. In a ferromagnetic material, regions called domains form. Within each domain, millions or billions of atomic spins are aligned in roughly the same direction. Different domains may point in different directions, so a piece of iron might not appear magnetized overall. When an external magnetic field is applied, the domains can grow or reorient, causing the material to become magnetized. The magnet you place on a refrigerator is the macroscopic result of this domain alignment. Other types of magnetic behavior also stem from spin. In paramagnetic materials, atoms have unpaired spins, but the interactions between them are too weak to cause permanent alignment. When an external magnetic field is present, the spins tend to align slightly with it, producing a weak attraction. Once the field is removed, thermal motion randomizes the spins again. In diamagnetic materials, all electrons are paired, and magnetism arises only from tiny induced currents in orbitals, leading to a very weak repulsion from magnetic fields. Spin, Electron-driven magnetism plays a crucial role in technology. Electric motors and generators depend on magnetic fields interacting with electric currents. Transformers, speakers, and magnetic sensors all rely on materials whose magnetic properties come from electron spin alignment. The storage of information in traditional hard drives uses magnetic domains to represent bits, with the direction of magnetization encoding zeros and ones. Behind the scenes, electron spins are being manipulated and stabilized. Magnetism is not limited to solids. In medical imaging, the magnetic properties of nuclei, also related to spin, are used in magnetic resonance imaging. Though this involves nuclear rather than electron spin, the underlying principle is similar: intrinsic angular momentum coupled to magnetic moments. The ability to detect and control spin interactions with magnetic fields allows doctors to produce detailed images of the inside of the human body. The relationship between spin and magnetism also extends into cutting-edge research. In spintronics, scientists aim to use electron spin rather than just charge to carry information. Devices are being designed where the orientation of spins can be controlled, transported, and detected, potentially leading to faster and more energy-efficient electronics. Quantum computers may use spin states as quantum bits, exploiting their ability to exist in superpositions. At a deeper level, magnetism illustrates how quantum rules scale up to the visible world. The alignment of spins in a magnet is a collective quantum effect. Each electron follows quantum laws, yet their interactions produce a stable macroscopic field that obeys classical equations of electromagnetism. This bridge between quantum and classical behavior shows how intrinsic properties at the smallest scale shape familiar forces. Temperature plays an important role in this balance. Thermal motion tends to randomize spin orientations. In ferromagnetic materials, there is a critical temperature above which thermal agitation overcomes the exchange interaction, and the material loses its permanent magnetism. Below this temperature, order emerges from quantum interactions. The transition reveals the delicate interplay between quantum alignment and classical disorder. Through all these phenomena, spin acts as the fundamental source of magnetic behavior. Without spin, electrons would not have intrinsic magnetic moments, and the rich variety of magnetic materials would not exist. The simple binary nature of spin, up or down relative to a direction, becomes, in large numbers, a powerful organizing factor. It allows matter to exhibit long-range order, respond to fields, and store information. What begins as an abstract quantum property thus manifests as a force you can feel, and a technology you use daily. The magnets on a fridge, the motors in appliances, and the data in storage devices all depend on the collective dance of spinning electrons. Magnetism is one of the clearest demonstrations that the invisible quantum world is not separate from everyday life, but forms its foundation. When electron spin was first proposed, it seemed like an abstract solution to a narrow puzzle in atomic physics. Few could have predicted that this subtle quantum property would eventually sit at the heart of major technologies that shape modern life. What began as a correction to spectral theory became a tool for seeing inside the human body, storing digital information, and designing the next generation of electronic devices. The path from quantum theory to practical invention reveals how deeply the concept of spin has woven itself into technology. One of the most profound applications lies in medical imaging. Magnetic resonance imaging depends on the spin of atomic nuclei, especially the hydrogen nuclei abundant in water molecules in the body. Although this involves nuclear spin rather than electron spin, the underlying principles are closely related. Both types of spin carry magnetic moments and respond to external magnetic fields. In an MRI scanner, a powerful magnetic field aligns many nuclear spins in the body. Radio frequency pulses then disturb this alignment, and as the spins return to equilibrium, they emit signals that can be detected and converted into detailed images. The ability to manipulate and measure spin states allows doctors to observe soft tissues non-invasively, revolutionizing diagnosis. The development of MRI required decades of research into how spins behave in magnetic fields, how they interact with their environment, and how their signals can be detected with precision. Concepts such as spin precession, resonance, and relaxation times are rooted in quantum mechanics. Without the understanding that particles possess intrinsic angular momentum and magnetic moments, such technology would not exist. A theoretical property discovered to explain atomic spectra became a life-saving medical tool. Electron spin also plays a central role in the storage of information. Traditional hard disk drives store data magnetically. Tiny regions on the disk surface are magnetized in different directions to represent binary information. These magnetic orientations arise from the collective alignment of electron spins in the material. Writing data involves using magnetic fields generated by electric currents to flip the orientation of spins in small domains. Reading data involves detecting the magnetic fields produced by those domains. Each bit of information ultimately corresponds to the quantum states of many electrons. As devices shrank and data densities increased, scientists began to explore more direct ways of using spin. This led to the field of spintronics, short for spin electronics. Conventional electronics rely only on the charge of the electron, moving charges through circuits to create currents. Spintronics seeks to use the spin degree of freedom as well, adding a new layer of control. Because spin can represent information through its orientation, devices can be designed where information is stored and transmitted using spin states rather than just charge flow. A key breakthrough in spintronics was the discovery of giant magnetoresistance. In certain layered materials, the electrical resistance changes dramatically depending on whether the spins in adjacent layers are aligned or opposite. This effect made it possible to build extremely sensitive read heads for hard drives, greatly increasing storage capacity. The 2007 Nobel Prize in Physics recognized this discovery, highlighting how quantum spin effects could have enormous technological impact. Spin-based memory devices are also being developed. Magnetic RAND access memory uses magnetic states, determined by spin alignment, to store bits. Unlike conventional memory, it can retain information without power and can operate quickly with low energy consumption. Such technologies show how manipulating spin directly may overcome some limitations of charge-based electronics, such as heat generation and energy loss. In more advanced research, electron spin is a candidate for the basic unit of information in quantum computers. A quantum bit, or qubit, can exist in a superposition of spin-up and spin-down states. This allows quantum computers to perform certain calculations in ways that classical computers cannot. Controlling spin coherence, maintaining delicate quantum states without disturbance, is a major challenge, but progress continues. The fact that spin can be isolated, manipulated with magnetic or electric fields, and measured makes it a promising platform. Spin also plays a role in sensors and navigation. Devices based on spin properties can detect extremely small magnetic fields. Such sensors are used in industry, research, and even space exploration. The precision of these measurements relies on understanding how spin states shift in response to external influences. Again, a quantum property provides a bridge between microscopic behavior and macroscopic function. The influence of spin extends to fundamental components of electronics. In semiconductors, the behavior of electrons in materials depends not only on charge, but also on spin interactions. Spin-orbit coupling, an effect arising from the combination of spin and motion in electric fields, influences how electrons move through materials. This effect is crucial in modern materials science, including the study of topological insulators and other novel states of matter with potential applications in electronics and quantum devices. What makes these technologies remarkable is that they rely on controlling something that cannot be seen directly. Engineers design systems to manipulate intrinsic angular momentum, an abstract quantum property, yet the results are tangible: images on screens, data stored in memory, machines in motion. The path from theoretical physics to everyday tools illustrates the power of understanding fundamental principles. Spin-based technologies also highlight the importance of precision measurement. The magnetic moment associated with spin is small, so detecting and controlling it requires sophisticated instruments. Advances in cryogenics, materials science, and electromagnetic control all played roles in turning spin from theory into application. Each improvement opened new possibilities, from better imaging resolution to higher data densities. At a broader level, the technological impact of spin demonstrates how basic research can have unforeseen consequences. The scientists who first studied spectral line splitting were not aiming to build medical scanners or advanced memory devices. They were trying to understand nature at its most fundamental level, yet the knowledge they uncovered became a foundation for innovation decades later. Spin serves as a reminder that the boundary between pure science and practical technology is fluid. A concept that once seemed purely theoretical now underlies tools that affect millions of lives daily. From hospitals to data centers, from laboratories to consumer electronics, the quantum property of spin quietly performs essential work. In this way, electron spin exemplifies how deep physical principles shape the modern world. What began as a mysterious feature of atomic spectra evolved into a cornerstone of advanced technology. The invisible angular momentum of tiny particles has become a powerful resource, harnessed through human ingenuity to explore, heal, compute, and communicate. By the early 20th century, physics had already undergone revolutions, yet the discovery of electron spin forced an even deeper change, one that reached beyond equations and experiments into the very way scientists understood reality. Spin did not simply add another property to the list of things particles possess. It challenged the assumption that every physical quantity must correspond to a picture drawn from everyday experience. In doing so, it reshaped the conceptual foundations of physics. Before quantum mechanics, most physical properties were tied to clear images. Position meant where something was, momentum meant how it moved, rotation meant an object turning in space. Even electric charge, though invisible, could be imagined as a substance that flowed. Spin broke this pattern. It carried the mathematical features of angular momentum, but did not arise from spatial rotation. The term survived, but the familiar picture did not. Physicists had to accept that the universe includes properties that cannot be fully visualized. This shift marked a departure from classical realism. The idea that physical objects always have definite properties independent of observation. In quantum mechanics, the spin of an electron along a given direction does not have a definite value until measured. Instead, the electron can exist in a superposition of possibilities. Measurement does not merely reveal a pre-existing value, it plays a role in producing the outcome. Spin experiments made this feature of quantum theory especially vivid. Consider measurements of spin along different directions. If an electron is prepared in a state with spin up along one axis and then measured along a different axis, the result becomes probabilistic. Repeating the experiment yields a distribution of outcomes rather than certainty. This behavior cannot be explained by assuming the electron secretly carried definite spin values for all directions. The mathematical structure of quantum mechanics, confirmed by experiment, rules out such classical hidden variables under broad conditions. Spin thus became a central example in debates about the nature of reality. The famous thought experiments and theorems of quantum foundations often involve spin systems. Because spin particles have only two possible outcomes in a measurement, they provide the simplest setting for exploring entanglement and non-local correlations. When two particles are prepared in a joint spin state, measurements on one can be strongly correlated with measurements on the other, even when separated by large distances. These correlations exceed what classical physics allows, a result confirmed by numerous experiments testing Bell's inequalities. Such results forced physicists to rethink notions of locality and separability. The behavior of entangled spins suggests that quantum systems cannot always be described as independent parts with their own local properties. Instead, the whole system can have properties not reducible to those of its components. Spin, as a discrete and easily controlled degree of freedom, became a key platform for revealing this interconnectedness. Spin also changed how scientists viewed symmetry. In classical physics, symmetries such as rotations and translations were seen as geometric features of space and time. In quantum theory, symmetries are expressed through mathematical transformations of wave functions. Spin arises directly from how particles transform under rotations. The existence of half-integer spin showed that nature allows representations of symmetry groups that have no classical counterpart. This deepened the link between mathematics and physical reality. The realization that particles are classified by how they transform under symmetries rather than by mechanical structure marked a conceptual turning point. Spin became part of the definition of a particle species. This perspective paved the way for quantum field theory, where fields and their symmetry properties are primary, and particles appear as excitations of these fields. In this framework, spin is not an extra feature but a built-in aspect of the field's nature. Spin also influenced philosophical discussions about identity. Electrons are indistinguishable. There is no meaningful way to label one as permanently different from another. Yet spin allows them to occupy different quantum states. The interplay between indistinguishability and distinguishable states challenges classical notions of individuality. Particles in quantum mechanics are not little objects with histories in the usual sense, but entities defined by states in a shared mathematical structure. Another profound impact of spin lies in the connection between microscopic rules and macroscopic reality. The Pauli exclusion principle, rooted in spin, explains the stability and structure of matter. Thus, an abstract quantum property determines why matter occupies space and resists compression. The solidity of the chair you sit on is linked, through a chain of reasoning, to the half-integer spin of electrons. This connection between the most fundamental level and everyday experience reshaped how physicists think about emergence. Spin also contributed to the breakdown of determinism. In classical mechanics, if one knows the initial conditions precisely, future behavior is determined. In quantum spin measurements, even complete knowledge of the state yields only probabilities for specific outcomes. This inherent randomness is not due to ignorance, but is built into the theory. The unpredictability of individual spin measurements became a symbol of the probabilistic nature of quantum events. Over time, these insights altered the goals of physics. Rather than seeking mechanical models for all phenomena, physicists embraced abstract principles such as symmetry, quantization, and invariance. Spin exemplified how these principles could predict new properties without relying on intuitive pictures. The success of this approach encouraged the development of increasingly sophisticated theories where mathematics leads and intuition follows. Spin thus helped redefine what it means to understand something in physics. Understanding no longer required a visualizable mechanism, but a consistent mathematical description that matches experiment. The acceptance of spin as fundamental showed that reality might be structured in ways that human senses and everyday metaphors cannot fully capture. In reshaping ideas about measurement, symmetry, identity, and determinism, spin played a role far beyond its initial context. It became a gateway into the strange but coherent logic of the quantum world. By forcing physicists to abandon certain classical expectations, it opened the door to a more general and powerful framework for describing nature. Through this transformation, spin helped move physics from a picture-based science to one grounded in abstract structure and empirical consistency. It revealed that the universe can contain properties that are neither visible nor mechanical, yet are essential for the coherence of the whole. In that sense, the discovery of spin did not just solve a problem in atomic spectra. It reshaped the philosophical and conceptual landscape of modern physics.